Hi, welcome to another video. So I've just recently got this LED matrix, 64 LEDs, actually red, green and blue. I've not used the green. I've got it wired up to a Texas Instruments 16 channel LED driver with dot correction and grayscale PWM. But for simplicity I'm just using the dot correction. Now many of you might have come across this LED driver before. You may realise it needs 6-bit SPI. A lot of the compilers out there only run 8 and 16-bit. That's of course you've got a PGA and you can develop your own. I'll show you the basics how I got this going. I'll let this run through the pattern again. There's just random patterns. And then YouTube. So that's the matrix. I think I've purchased 2 of them off eBay. About £8, including shipping. I'm running it off an 8-bit microcontroller. That particular chip is the PIC 18F46K22. I've taken off the crystal and I'm running it on the internal 16 meg oscillator, multiplied by 4 times with a PLL. So it's running at 64 megs. And the chip at the back, that's the tiny surface mount. There are other packages available. That's the surface mount TLC5941. And there's a closer look at it. That's the device, 16 channel LED driver TLC5941. I'll show you the pictures on my PC. So that's the device I've got, and you see the thermal pad shown underneath. Look at these 16 outputs, so 0 to 15, 16 outputs. I've wired them, these to red, this side to red, and this side to blue. And if I scroll the picture up. Right, so before I move this out of the way, we've got red, green and blue. And up there, red, green and blue. So this is the power to this side, power to all the anodes, the 64 LEDs. I've run them off port D, so that's just power in. And then scrolling up to the top, hopefully you can see the colour. Doesn't look particularly good on this camera monitor. Got the red coming up to the first 8 bits of the TLC driver, and the blue coming over to the second 8 bits. So actually these are the most significant bits, so it's 15 down to 0. So that's the LED wiring. If I show you the PIC wiring and the other bits. So hopefully you can see, I'll get the important ones out of the way first. So this IREF, that's the current reference resistor for the LEDs. I think I've got something like a 1.3K, but 1.2 to 2K if you're running on sort of 5 volts. This chip says 3 to 5 volts, but my device actually works down to 2.7. So VCC, that's the current resistor. Test, it says should be wired to the supply. Grayscale clock, I'm using dot correction, so you can just wire that to the supply. Ground, a blank pin, I've got to RA0. The X latch, or X lat, that's a latch to latch the data in. I've got wire to RB4. Serial clock, I've got an RC3. That's a serial in 6-bit words. I've got an RE2. The mode you can wire to the supply. If you're changing the mode to grayscale, you need to pull it down to ground, so that's why I've actually got it running to the PIC as well. So on the PIC itself, just master clear 4K7 to the supply. Power and ground, no crystal. And you can see there, I'm using port D, so 8 pins driving the anodes of the LED. Hopefully that makes sense. Right, if you're not familiar with 8-bit SPI, this will help, because this chip wants 6-bit SPI. So that's 6 clock cycles. This is the most significant cycle up here. 5, 4, 3, 2, 1, 0, so 0 to number, so that's our 6 clock cycles. You see, most significant bit. Now when we add the data, depending on where the data comes on in relation to this clock cycle, will determine the SPI data out. This bit's really for beginners if you're totally not familiar with SPI, so these are just the clock cycles again. And I've got a video on SPI, so 0 to 5 clock cycles, so 6 clock cycles. If we selected the data here, we've got a bit value of 1, 2, 4, 8, 16, 32. And if we select them all, you add up those numbers. So here's an example of what I'm doing with the code. Incidentally, I'm using Microelectronica's Micro C Pro for PIC. So this is compatible with the Arduinos, everything out there, all the 8-bit microcontrollers. So we've got these binary values. Here's our 6 clock cycles. I'm turning on the data here and turning off after the last clock cycle. So looking to the right, 32 plus 16, etc., etc., equals 63, or hexadecimal 3F. And incidentally, again, that 63 is the maximum value this TLC chip will take on dot correction. You can't have anything higher than 63. If you start running more clock cycles into it, the most significant bits are dropped off, because it wants the most significant bits first. So again, for the beginner, if I turn the data on here and off here, we've got a value of 1. Moving down the picture. In case you're not familiar with SPI again, you can sample the data at one of the edges or in the middle. Right, for 16 LEDs, this is what I'm doing. I'm just bit banging, turning this port on, running that 6 times, turning the data off, another 6, turn it 16 times to get 16 LEDs on, or whichever LED I want on. If I just want one LED on, like the 15th most significant, which on this screen would be blue, I'd run this once and then just 15 lots of 6 clock pulses with no data. That just give me this one LED and nothing else. You've still got to run all these clock cycles. Run this once, then this, run the clock cycles 15 more times to fill up the register before you latch it in, so it knows what LED to turn on. Most compilers using SPI will give you 8 clock pulses for 8 bits of data, and that'll be 1 to 128. But as I said, this TLC Texas Instruments chip wants a 6-bit word, so you can only run in 6 clock pulses. Any more, the data becomes corrupt. So if I show you, for example, using Microelectronica's software, which is 8-bit SPI and you can't change it, if I run in 8 clock pulses, but just select the last 5, because of these 2 clock pulses here, I don't want to select these bits, I just want all of these. I run them in, it's interfering with the next 2 most significant bits. And that's going to keep on happening. So the chip's going to look for 6 plus 6 plus 6 plus 6. If you keep on running in 8, 2 bits of data are going to be missing somewhere. And what happens, you just get random patterns on the matrix and not the particular LEDs you want lit. If I run 12 strings of 8 to give me my 96 bits, you can see I've got 2 bits of data are going to be blank in every single word. I don't think I've explained it very well, but hopefully that makes sense. So you can see I've got a note there, 8 clock pulses, but I'm only selecting the last 5 bits. You can see, so it's the same value, but the effect can be seen on the next 2 most significant bits. And when you send this 16 times, A, it's too much data, and B, you're knocking off the most 2 significant bits of the next LED. So you can see there, the chip would actually be looking for the most significant bits, which are here, which are actually blank. But if we chop these off, then all of a sudden the most two significant bits are on. So you've got more notes. Most significant bit is 0 and bit 6, 2, so 7 and 6. The first LED would have a value of 15 and should be 63. The max value for dot correction, which I've previously mentioned, is 63. See page 17 of the data sheet. So bit 6 and 7 are too high. So if there's no permutation of these clock pulses, that will give you a value of 63. But in case you missed it, on 8-bit SPI, this pulse by itself is 64, so that's too high. And this pulse here would be 128 by itself. But regardless, it's still got 8 clock pulses, so that just screws everything up. You need 6. Just a few more notes. So if you're able to send the first 6 bits of an 8-bit SPI, the last 2 empty clock pulses still interfere with the next expected 6 bits, again reducing the value wanted. If you use 8-bit SPI, you can only send 8 bits 12 times, so 12 times 8, 96 bits, which is needed by the chip before you latch in the data. So grayscale data is a 12-bit word per channel, so you've actually got to clock in 192 bits before something happens. So as I say here, you can either have bit bang or get an FPGA to do the job. Right, this is Microelectronica's Micro C Pro for PIC. I'm using the 18F46K22, running on the internal oscillator 16 megs and the PLL, which gives us 64. I've got various chars and ints. I'm using this matrix here. This is initializing a timer. Every 100 milliseconds we get an interrupt. A couple of chars for the counters. This is the interrupt. So clear the flag, and then you can see the matrix counts 1 here. So every time the interrupt comes along, that keeps on counting up. So for the first routine, look at port D here. I'm starting with pin 0 on the right here is 1. That gives us the red LED moving from the right to the left down here. And then when the matrix gets to 8 to 16, it just goes the other way. But you can see I've inverted this lot. Instead of 0 to 7, it's 7 to 0. So the first LED goes from right to left and left to right. Right, so just before I go to the main, I've just had a quick thought in case you all start jumping on saying no, I'm wrong. This is just a guide. If you're sending 8 clock pulses, obviously 2 of the clock pulses, most significant bits, are going to be empty, and when you start shoving them down the chain, 2 bits are going to get knocked off. So I might have this back to front. It might be the most 2 significant bits are wiped off, or the last 2 of the preceding pulse. I forget to which. Need to look at the data sheet, but that was only a guide. So it's really, this device needs 6 clock pulses and not 8. So don't read too much into that. If I'm back to front, my mistake. Right, so this is the main. This is the OSCON register, setting the first 3 bits to 1. These are the available frequencies on a 46K22. This is an alternative way of setting the OSCON bits. Just set those 3 bits. This is important. PLL enable multiplies the 16 megs by 4 to give you 64 megs. Initialize a timer. All the outputs digital. Right, so this is when I was messing about with the PWM. I've obviously disabled the SPI, clearly doesn't work. This is the RA1 for the mode, see a note down here. Ground for grayscale and VCC for dot correction. That was latching that in if I then wanted to change it to grayscale. This is RC2, so that PWM output, but I've got it tied high, not using PWM. And this is the wire 1. So if the counter 2 equals 0, show matrix 1. So I forget the first 8 blue LEDs, show the first red LED on the first line, then the second line, third line, so that's bit 0, 1, 2, 3, all the way down to 7, then some random patterns. So when the counter equals 14, show the YouTube text, and then when the counter is greater than 20, 0 all the counters. Right, this is the first routine. I may have got the others back to front. So I've got 90 clock pulses, so that's 15 empty LEDs, 15 not shown, and then 1 LED shown. And then you put in the data and latch it in at the bottom. So if I just clarify some of this, when I initially got this working, I had to delay 1 microsecond. The whole routine would take about 12 microseconds, which is a bit too long. I messed about with the delay cycle, and that was greater than 1 microsecond. So then I eventually ended up using this ASM NOP. And if you're not familiar, ASM is assembly, NOP is no operation. That's the smallest delay on this 18F46K22 running at 64 megs. And that ASM NOP will give you 129 nanosecond delay. So one 6-bit word is written in 1.62 microseconds as opposed to 14 microseconds with a 1 microsecond delay. So that just made everything quicker and smoother. You divide 90 by 6, that will give you 15. So 15 LEDs aren't on. Then I'll turn the data on, which is RE1. Small delay. Then there's 6 clock pulses. And then down the bottom, turn the data off, just like I showed you in the drawing. Once that's happened, you've got 96 bits of data. You latch it in. And that's the end. That's the end of that routine. So matrix 2, I just decreased the amount of empty LEDs first, so I've only got 84 clock pulses. So you can see I must be coming down a row. So I'll turn on this LED, bit 1, so not bit 0, bit 0, bit 1, and then another empty clock pulse. So you can see I'm shifting the LED down, latch the data in, and you see there's 78. One bit of data, a bit 2, that's LED 2, down another row, then 2 lots of clock pulses, so 12 clock pulses, that's 2 lots of data for 2 LEDs, so 2 doing nothing, latch, and you can see here I started becoming familiar, so there's 72 clock pulses, just a confirmation that's the clock and that's the data out, and that's the data, just doing it once. So the RE1, ASM NOP, 6 clock pulses, you can see there, I is less than 6, and then 18 clock pulses, so that's 3 LEDs that are blanked out after the data. So you can see I'm down to row, bit 3 is row 4. Hopefully you get the idea, and then latch the data in. That's simple. So for the last part of the code, I'll show this letter B. So let's just concentrate on the right hand parts, these 4 zeros here, the outermost part of the B. So we've come down 8 LEDs, which are blue, then another red one here, another red one here. So that's 10 lots of LEDs I don't want on. So that's 60 clock pulses, remembering its most significant bit first, so 15 down to 5. So we've actually got 10. The 6 and 7 plus the other 8. That's 60 clock pulses. Then we want these 2 bits on, which are these 2 bits here. Then we've got an empty clock pulse down the bottom, which is this empty part here. Then we want these 2 bits and then nothing. So scrolling down, that's the empty bit in the middle. That's the last 2 bits of data on. And that's the last LED, which is the top of the display. And then, so that's 96 bits of data, and you latch it in. That's it. And just so you don't all start shouting, well, how am I moving the text? This is the beginning of the U for the YouTube. So I blank the display, and you can see, so I'm asking for the vertical part of the U, and then showing it on position 1 of the port, waiting 30 milliseconds, blanking the display. This is the second part of, this is the horizontal lower part of the U. This is the vertical part of the U, and this is the horizontal part of the U. So delay, delay, so I'm showing nothing on the bottom and moving in the vertical line. Then come down, I'm selecting the vertical line and shifting it in one. And then the bottom of the U starts coming in. So 30 millisecond delay, 30 millisecond delay, and you can see I'm just shifting it over. Select the matrix 12, which is the vertical, and then select matrix 13, which is the horizontal. So now you can see 2 bits of the bottom of the U have come in there, and meanwhile the vertical is shifted in 3 places. And blanking the display every time, and so I'm moving the vertical in there, and that's all of the horizontal there. So looking at this one, the bottom of the U was only 3 LEDs. You'd expect the next one to only have 3 ones and a 0 after. So scroll down. So that's 2 parts of the U. The vertical is there, and that's the bottom. Hopefully that makes sense. So with this you should be able to figure out a pattern and get some text yourself. So this video could go on forever, but I want to show you the basics. Now you know how to bit bang make up your own SPI, whether it's 6-bit, 12-bit, 18-bit. You can figure out how to do it now and get one of these matrix displays working. Incidentally, which I haven't had time, if I tie a second one of these chips into the circuit, I can get my second matrix to work. And the wiring on the bit on the back, just these pins joined to various lines. As I say, these are red, green and blue, but I'm not using the green. If I wire the second chip up, I can get the first 8 bits to bring on the green and the second 8 bits to bring on maybe the reds, greens or blues on here. So Happy New Year, YouTube. Hopefully all this makes sense. Thanks for watching. Thank you very much.